Hi guys, this is Vijay and I hope you are doing well. In this video lecture we will discuss on basic topics of thermodynamics, steady flow energy equation and conservation of mass principle. It is also known as continuity equation. Let us start with first law applied to a process. According to the first law statement, we cannot generate the energy and we cannot destroy the energy, but whatever the energy available in nature, they all are convertible with each other. The first law of thermodynamics is oftenly applied to a process as the system changes from one state to another. For any system and in any process, the first law can be written as Q equal to delta E plus W. It is called equation 1. It is also written as delta E equal to Q minus W. It is called equation 2, where delta E means it is the sum of internal energy plus kinetic energy plus potential energy plus other forms of energy equal to net change in total energy of the system. In differential form, first law of thermodynamics for a process can be written as delta Q minus delta W equal to change in internal energy. It is called equation 3. Also for a cyclic process, delta U equal to 0. In a cyclic process, the system return to its initial state and so the internal energy not change. The heat added to the system equal to the work done by the system. Hence Q minus W equal to 0 for cyclic process. So Q equal to W. Now we will discuss conservation of mass principle and it is also known as continuity equation. According to the conservation of mass principle, it states that the mass of a system can neither be created nor destroyed, but its amount remain constant during any process. It only changes its form, or we can say phase. By the conservation of mass, if there is no accumulation of the mass within the control volume, the mass flow rate entering must equal to the mass flow rate leaving. So here M1 equal to M2. The conservation of mass principle for a control volume can be expressed as total mass entering in a control volume minus total mass leaving in a control volume equal to net change in mass within the control volume. The amount of mass flowing through a cross section per unit time is called the mass flow rate and it is calculated as m dot equal to AC divided by small v. Okay, so basically in thermal we are considering two types of flow rate, mass flow rate and volumetric flow rate. So generally in case of a steam turbine we are considering mass flow rate. In some of the cases we are considering volumetric flow rate, and the unit of mass flow rate is kg per second and the unit of volumetric flow rate is meter cube per second, and it is also known as discharge. So m dot equal to AC divided by V. It is called equation 5, where m dot means mass flow rate in kg per second, A is the cross sectional area of flow in meter square, V means specific volume of fluid in meter cube per kg, and here we are considering C equal to fluid velocity in meter per second. But we know that specific volume means it is the reciprocal term of density, because the unit of specific volume is meter cube per kg and the unit of density is kg per meter cube. So specific volume and density both are the reciprocal term. So we can also write specific volume equal to 1 upon rho. So put the value of specific volume in equation 5. So equation 5, it is also written as m dot equal to rho AC, or in some of the reference book it is written as rho AV. V means velocity of fluid, small v means it is the specific volume of the fluid, but here we are considering C equal to fluid velocity. It is called equation 6. The volume flow rate through a cross sectional area per unit time, it is also known as discharge, and its unit is meter cube per second. So it is also written as Q equal to A into C, and in some of the reference book it is written as Q equal to A into V, where C and V, it is called velocity of fluid. For a steady flow, m dot equal to constant means we can say that whenever we apply the continuity equation for any of the flow process, so it is written as m dot equal to rho a v1 c1 equal to rho 2 a2 c2. It is called continuity equation, and it is applicable for flowing fluids. It is called equation 7. Now we will discuss what is steady and unsteady flow process. A flow process is said to be steady when the fluid parameters at any point of the control volume remains constant with respect to time. The parameter may, however, be different at different cross section of the flow passage. So for that, del P by del tau equal to 0. Okay, it is called steady flow process. So in steady flow process, the fluid parameter at any point of the control volume remains constant. Here P is the parameter of the fluids. Where a flow process is unsteady when the conditions vary with respect to time. So for that, del P by del tau is not equal to 0. It is called unsteady flow process. Now we will derive steady flow energy equation. Here we are considering some of the assumptions whenever we derive this equation. So these are the assumptions are made in the steady flow system analysis. Our first assumption is the mass flow through the system remains constant. So here we are considering m1 equal to m2, where m1 is the inlet mass of fluid and m2 equal to outlet mass of fluid. Our second assumption is fluid is uniform in composition. Okay, throughout the control volume, the composition of the fluid will remain same. Our third assumption, the only interaction between the system and surroundings are work and heat. Our fourth assumption, the state of fluid at any point remain constant with respect to time. So here we are considering steady flow. And our fifth assumptions, in the analysis only potential, kinetic and flow energies are considered. Okay, there are various types of energy. Okay, whenever we apply the first law of thermodynamics to any of the process, okay, we have already discussed in our previous slides. Okay, we are considering internal energy, kinetic energy, potential energy. There are different forms of other forms of energy, but here in the analysis we are considering only potential energy, kinetic energy and flow energies are considered. Here we consider a flow of fluid through an open system as shown in figure. During a small time interval dt, there occurs a flow of mass and energy into a fixed control volume. Entry is at section 1 and exit occurs at section 2. The fluid enters the control volume at section 1 with average velocity c1, pressure p1, specific volume v1 and specific internal energy u1. Same as the corresponding values at the exit section 2 are c2, p2, v2 and u2. Here we are considering. Further, during the fluid flow between the two selected sections, heat and work may also cross the control surface. The following energies are taken into account while drawing up the energy balance. First one is the internal energy stored by the fluid. Second one is kinetic energy equal to 1/2 mv square or 1/2 mc square. Third one is potential energy equal to mgz. Fourth one is flow work. Here we are considering flow work equal to P1 V1. And fifth one is heat interaction. Sixth one is work interaction. It is also known as shaft work. So according to the first law of thermodynamics, we cannot generate the energy and we cannot destroy the energy, but whatever the energy available in nature, they all are convertible. So according to the energy balance in symbolic form may be written as M1 in bracket U1 plus P1 V1 plus C1 square by 2 plus GZ1 plus Q equal to M2 in bracket U2 plus P2 V2 plus C2 square by 2 plus GZ2 plus work done. Okay, so according to the first law of thermodynamics, we cannot generate the energy and we cannot destroy the energy, but whatever the energy available in nature, they all are convertible. Okay, so here we are considering internal energy U1 and flow work is P1 V1. Here we are considering kinetic energy at inlet side C1 square by 2 whenever it is multiplied with M1, so 1/2 mv square or mc square by 2 plus mgz So same for corresponding values at exit side. So above equation is the general steady flow energy equation, and it is equally applicable to compressible and incompressible fluid, as well as ideal and real fluids, liquids and gases. But according to the assumptions, our first assumptions, here we are considering mass remain constant. So m1 equal to m2 equal to m, and we know that enthalpy means it is the sum of internal energy plus the product of pressure into volume. So H equal to U plus PV. So put the value of M equal to M1 equal to M2 and H equal to U plus PV in this equation. So further we simplified this equation. Here we put the value of enthalpy instead of H equal to U plus PV, and here we are considering M1 equal to M2 equal to M. Okay, so this is our simplified equation. Steady flow energy equation on unit mass basis. Okay, so we can also write this equation on unit mass basis. H1 plus C1 square by 2 plus GZ1 plus Q equal to H2 plus C2 square by 2 plus GZ2 plus work done, shaft work. Here all the terms represents energy flow per unit mass of the fluid, and its unit is joule per kg. In next lecture we will discuss various applications of steady flow energy equation in engineering. Applications like as a turbine, heat exchanger, we can also apply it on nozzle, diffuser. We will discuss it in our next lecture.